Similarity is actually one of the most applicable to real life content areas that we've studied so far. So similarity is all about finding the lengths of buildings, of poles, of lakes without actually measuring these items. So similarity is really useful because it's how can you find how tall something is, how wide something is without actually measuring it. So if you have an object that can't be measured, similarity is really the only way to do it. We'll learn some other tricks about other ways, but similarity is going to be one of your go-tos. For this project you're doing where you're trying to find out the lengths of objects before you actually measure them, you're going to need to use similarity to do so. There are many reasons to do this. Maybe the object it's not possible to find the length of it because maybe there's a giant mountain sitting on top and you're trying to figure out what that tunnel will be before you start drilling into the mountain. So it's not possible to find that length. Maybe it's too dangerous. Maybe you don't want to climb a building to figure out how tall it is. Or maybe it's just something that's too tall. Maybe you're trying to figure out how tall a really tall tree is and you can't climb that high. So lots of reasons to do this. There are two ways that you'll see these problems. You'll see them as either two separate triangles, like this, or as one triangle within another. And if you look at the last video, there's some examples of how we can solve each one. One common format where you'll see these problems is where you'll be asked about how tall something is, and you'll be given a shadow length. And these I'm going to refer to as shadow problems. And they're quite common in similarity and applying it because it's an easy way to do so. So when you're using shadow problems, you use the rays of the sun. Think about the rays of the sun, and that's what I marked in green here. Those are going to be the hypotenuses for your triangles. So we don't have triangles, right? We have a building, we have a flagpole, and we have a person. But we can make triangles here in order to figure out how tall each of these objects are. So again, a building, flagpole, and a person, all different heights, but the sun is going to hit them at the same angle. Notice that all of these sun rays, they're parallel. Sun rays will always be parallel. That's why we use shadow and the sun and not like a spotlight, for instance. Because if I have a spotlight over here, it's not, by the time it comes over to this person, it's going to be at a different angle. But the sun is about the same. So if I look at just this building for a second, I've created a triangle just from one object, the building. I have the building, I have its shadow, and I have the sun ray. And I've created sort of a triangle. We need to make some assumptions when we do this. The first and the biggest one, well, we've already assumed that sun rays hit objects at the same angle. So if they hit objects at the same angle, that means that I'm hitting this object at the same angle as I'm hitting the flagpole, and at the same angle that I'm hitting the person. So all of those angles at the top of these triangles will be congruent. I'm also assuming that the ground is flat. I need to assume that the ground is flat in order for this, because if the shadow was down here, it would be much longer by the time it got to this right here if I was on a hill. So I need to assume that the ground is flat, making this a right angle. Now, I know one way that I can prove two triangles similar is by showing that two angles are congruent. I've just done that. The sun hits the object at a congruent angle. I'm also assuming that the ground is flat, so the object I'm also assuming that the object is sticking straight out of the ground. So if I'm a leaning person, this isn't going to work. I need to be standing as tall as possible. So the object and its shadow are perpendicular, forming a 90-degree angle in each case. Usually when you see the word shadow in a problem, you can go ahead and make these assumptions. I can also, once I prove two angles, I've proven similarity, but I can go a step further here just to say that not only is the sun hitting the sun not only hits objects at the same angle, but it also hits the ground at the same angle. So this angle is also going to be congruent to this one and to this one. Okay. Angle, angle, angle. These triangles are similar. So how you're going to see this is you're probably going to be asked to find the height of a really tall building, given things you know. So maybe you'll be given that this person is 6 feet tall and that their shadow is 4 feet. Maybe you'll be given that this shadow of the flagpole, because it's easy to measure a shadow, right? It's on the ground. You can use a tape measure. This shadow here, maybe this is 12 feet, and now I'm asked to figure out how tall is this pole, this flagpole. So I could set up a proportion here. Let's call it X for now. And I could say, I'm going to go from the person to the flagpole, but it doesn't really matter. I'm going to say 4 feet over 12 feet, that's the shadow of both of them, is equal to 6 feet over X. And now, so I have the shadow of my human over the shadow of the flagpole versus the height of the human, and now I need to find the height of the flagpole. So now I can solve this just by cross multiplying. I have 4x is equal to 72, and now x is equal to 72 over 4. Okay, 72 over 4, what is that? 40, 20, 18. So x is equal to 18. So this flagpole is 18 feet tall. If I knew to figure out the building, I would have to know either its shadow or the height, and I could find the other. Most likely you'll be given its shadow, and you'll need to find the height of the building. So in this case, maybe its shadow is 40 feet long, in which case, how can I figure out how tall it is? So let's do the same thing. I could either do it with the flagpole or with the human. I'm going to do it with the human because those numbers are smaller. So just like I did here, 4 feet is the shadow of the human over 40 feet is the shadow of the building, is equal to 6 feet over, let's call this one y. I can go ahead and reduce this before I even multiply across, and I know that this is going to be 1 foot for 10 feet. So now I have, multiplying across, I have 60 feet is equal to 1 foot times y, which is just y. So the height of this building is 60 feet tall. These are called shadow problems. You might also see them as triangles within triangles. These ones are really common, especially if you can't actually measure one of these lengths. So maybe this isn't the height of this tennis player and the ball, but maybe it is a lake or a mountain or something where you can't actually measure it. So here I have a tennis player. I want to figure out how high I need to hit this ball in order for it to just skim the net and land 6 meters across the net. So I've done some measurements already where I know I'm 12 meters from the net on my side. I want it to land 6 meters onto the other side, just going barely over the net. How high do I have to hit that tennis ball? My advice when you're doing these problems is to separate it into 2 separate triangles so you can keep the numbers straight between which ones are parts of the triangle, like this 12 meter here. That's just part of my bigger triangle. If I were to cut cut after that 12 meters, I would have a trapezoid, not a triangle. So it's important that we understand that so that our proportions are correct. So I always like to redraw it. So I redrew this little triangle here, the one inside the bigger one, 6 meters for the bottom, 0.9 meters as the net. Here I have, and again, this is my big triangle. I have 6 meters and 12 meters. So I have to add those together to get this bottom. I get 18 meters, and I still have h as my height. Now check and make sure that your triangles are similar. I know I have a right angle here. That's given. I also can assume that this net is at a right angle. So, from corresponding angles, I know that those are congruent. The fact that they are congruent means that, if corresponding angles are congruent, these lines are parallel. Okay, so my net and my height are parallel. They're both perpendicular to the ground. I also have an angle here with the reflexive property. This angle is in both of these triangles. So, knowing that that's a right angle in both and that these are congruent, I now have angle. I could also use corresponding to find those angles also congruent, but I don't need to. Now I need to set up a proportion to find h. I'm going to set up the bottom of my small triangle over the bottom of my large triangle is going to be equal to the height of my small triangle over the height of my large triangle. And again, there are so many ways to set up this proportion. So now I'm going to cross multiply and end up with 0.9 times 18 is going to be equal to 6h. And you guys can solve that on your own to figure out what h is. One thing you could do is you could also reduce these first. So this would become 1, this would become 3. That would make it a little bit easier. Then you'll end up with 0.9 times 3 is going to be equal to 1 times h, or just h. So you can plug this into a calculator. We could do it out. We're going to end up with 2.7 is equal to h.